Astronomers just finished mapping the largest physical structure in existence, a skeleton of galaxies, gas, and dark matter stretching across nearly the entire universe, and traced it back to a point in cosmic history when it should barely have existed at all. Instead, it was already there, already organized, already sprawling across billions of light years, less than 1 billion years after everything began. Stick around, because I'm going to walk you through exactly what the James Webb Space Telescope's largest survey ever conducted just revealed about the cosmic web, why the structure it found is considerably more built out than any model predicted this early, and why that discovery is quietly becoming one of the most significant challenges to modern cosmology in years. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the largest survey Webb has ever conducted. To understand why mapping this particular structure matters so much, you first need to understand what the cosmic web actually is, because it's not something you can point a telescope at directly and simply photograph. Astronomers use the term to describe the enormous, skeleton-like framework connecting galaxies across the entire universe, vast filaments and sheets made up of dark matter and diffuse gas, threading between galaxies and galaxy clusters, punctuated by enormous, nearly empty voids in between. Gravity is what builds this structure over time, slowly pulling matter along these filaments, concentrating it into dense knots where galaxies and galaxy clusters eventually form, while the voids in between grow emptier as everything nearby gets pulled toward the denser regions. It's the largest organized structure in existence, larger than any individual galaxy or cluster, essentially the scaffolding upon which everything else in the universe, including our own Milky Way, sits. One useful way to picture the cosmic web is to imagine a sponge or a mass of soap bubbles clustered together. The thin films and edges where multiple bubbles meet represent the dense filaments and clusters where galaxies actually form and concentrate, while the empty interior of each bubble represents one of the enormous cosmic voids, regions of space that have been slowly emptied out over billions of years as their matter drained away along gravity's pull toward the denser walls surrounding them. Some of these voids span hundreds of millions of light years across, nearly, devoid of any galaxies at all, standing in stark contrast to the comparatively crowded filaments and clusters that thread between them. That basic pattern, dense filaments separating enormous, nearly empty gaps, has been confirmed repeatedly in the relatively nearby universe using ground-based surveys over the past several decades. What remained genuinely unclear, prior to this new research, was exactly how early in cosmic history that same pattern first began taking shape, and how quickly it developed once it did. Mapping that structure requires an enormous amount of data, because a single galaxy tells you almost nothing about the cosmic web on its own. You need to know the precise three-dimensional position of hundreds of thousands of galaxies simultaneously, plotted against both their location in the sky and their distance from Earth, in order to actually see the underlying pattern of filaments and voids connecting them. That's precisely what a research team led by Hossein Hatamia, a graduate student at the University of California, from Riverside, working alongside physics professor Bahram Mobasher and the broader Cosmos collaboration, set out to accomplish, using the single largest survey Webb has ever conducted, appropriately named Cosmos Webb. If you're finding this as remarkable as the researchers involved clearly are, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. The Cosmos Webb project, led by Caitlin Casey at UC Santa Barbara and Jehan Kartaltepe at the Rochester Institute of Technology, was specifically designed from the outset to capture an enormous, contiguous patch of sky in exhaustive detail, rather than the smaller, deeper pinpoint images Webb typically becomes famous for. According to Casey, the goal was to construct a deep field of space on a physical scale that far exceeded anything previously attempted. Specifically, so researchers could study not just individual distant galaxies in isolation, but the broader cosmic environment those galaxies actually live inside. That distinction matters enormously. Most of Webb's famous early images captured spectacular but narrow snapshots, incredible detail packed into a tiny sliver of sky. Cosmos Webb instead prioritized breadth, covering enough total area to actually trace how galaxies cluster together and connect across enormous distances, the only way to meaningfully study the cosmic web itself rather than just its individual components. Casey has described the underlying motivation behind that design choice in terms that go beyond simply cataloging more galaxies for their own sake. She has explained that the cosmos is fundamentally organized into dense regions and voids, and that the team's ambition wasn't only to find the most distant, most extreme individual galaxies Webb could detect, but to place those galaxies into their proper broader context, understanding exactly what kind of cosmic neighborhood each one actually lived within. That framing matters, Because a galaxy studied in complete isolation can only tell researchers so much. Understanding whether a given galaxy sits within a dense, rapidly forming cluster, or out in the comparative isolation of a cosmic void, adds an entirely separate layer of information about how and why that particular galaxy evolved the way it did. Information no single deep, narrow image could ever hope to capture on its own. The results, published in the Astrophysical Journal in 2026, cataloged nearly 800,000 galaxies, reaching back across roughly 13.5 billion years, covering approximately 98% of the universe's entire history since the Big Bang. Atamnia's specific contribution built directly on top of that massive catalog, developing a detailed map tracing the cosmic web's filaments and clustered structures all the way back to when the universe was only about 1 billion years old, a technique that had genuinely never been possible in this much detail before, since earlier observations from the Hubble Space Telescope simply weren't sensitive enough to reliably detect and precisely place enough faint, distant galaxies to trace the underlying web connecting them. Here's where the finding turns from an impressive technical achievement into something that's actively unsettling researchers' existing models. Before Webb ever captured this data, Casey and her colleagues had made their own predictions, based on the best available theoretical models, about roughly how many galaxies they expected to find scattered throughout this early cosmic web. The actual data came back showing approximately 10 times more galaxies than anticipated in this early era, along with supermassive black holes that Hubble had never been sensitive enough to detect at all. That's not a minor statistical adjustment researchers can quietly absorb into their existing framework. A factor of 10 discrepancy between prediction and observation represents a genuinely significant gap, one that suggests either galaxies formed and organized themselves considerably faster in the early universe than current models account for, or that some part of the underlying physics governing how matter clumps together and ignites into stars during this era isn't fully understood yet. This particular finding connects directly to a broader pattern that's been building across multiple separate Webb discoveries over the past several years, rather than standing alone as an isolated surprise. Researchers have independently found individual galaxies from the same early era that appear far more massive, more mature, and more chemically complex than standard models predicted they should be capable of producing this quickly. A galaxy cataloged as ZFUDS 7329, for instance, was found containing more stars than our own Milky Way, despite forming only about 800 million years after the Big Bang, well before the specific dark matter halo formation process current models rely on should have had time to produce something that massive. Separately, in May of 2026, researchers led by Ben Forrest at UC Davis identified a massive early galaxy that shows essentially no rotation at all, a trait typically associated only with much older, more settled galaxies, far closer to our own cosmic neighborhood, not something expected to already exist when the universe was still in its infancy. Forrest's team specifically compared that non-rotating galaxy against two others from roughly the same era, and the contrast between all three turned out to be almost as informative as the anomaly itself. One of the three galaxies rotated in a fairly ordinary, expected way. Another showed a more irregular, chaotic internal structure, consistent with a galaxy still actively assembling itself out of infalling gas and merging smaller clumps. The third showed no organized rotation whatsoever, but instead displayed strong, essentially random motion among its individual stars, a dynamical signature researchers typically associate with galaxies that have already had enough time to settle and stabilize internally, a process that's supposed to take considerably longer than the roughly 1 billion years available to this particular object. Finding all three of these very different evolutionary stages already present side by side, this early in cosmic history suggested to Forrest's team that galaxy formation during this period was proceeding through a much wider and more varied range of pathways than researchers had previously assumed, rather than following one single predictable timeline. What the cosmic web mapping adds to that growing pile of individual anomalies is context, and it's context that makes the problem considerably harder to dismiss. A single, unusually massive galaxy might, in principle, be explained away as a rare statistical outlier, an unlikely but not impossible fluke sitting at the extreme tail end of an otherwise normal distribution. 10 times more galaxies than predicted, organized into filaments and clusters across an enormous representative patch of sky, is a much harder result to wave away using that same reasoning. It suggests the excess isn't confined to a handful of unusually lucky individual objects. It's baked into the broader structure of the early universe itself, at a scale large enough that it starts to look less like an outlier and more like a genuine gap in the underlying theory. It's worth being precise about what the gap actually implies and what it doesn't, because it's easy for a story like this one to drift into overstatement. This isn't evidence against the Big Bang itself, and it isn't evidence that the broader age or overall structure of the universe is fundamentally wrong. The foundational framework, describing how the universe began and has evolved since, remains solidly supported by an enormous independent body of evidence that has nothing to do with this specific finding. What's genuinely being challenged is something narrower but still significant: the detailed physics of exactly how efficiently matter collapsed into stars and galaxies during the universe's first billion years, and how quickly those early galaxies were able to organize themselves into the large-scale filamentary structure Webb just finished mapping in this much detail. Researchers studying this broader puzzle have proposed several possible explanations, none of which has yet emerged as a fully settled consensus answer. Some have suggested that star formation efficiency in the extremely early universe may simply have been far higher than current models assume, meaning gas clouds converted into stars faster and more effectively than anyone previously thought physically possible. Others have pointed toward the possibility that dark matter itself may have clumped together and organized into the scaffolding of the cosmic web earlier and more efficiently than standard cosmological models currently predict, which would mean the discrepancy points toward a genuine gap in researchers' understanding of dark matter's behavior during the universe's earliest chapter, rather than simply a gap in how quickly ordinary matter converts into visible stars and galaxies. There's also a more mundane possibility researchers are careful to keep on the table, since extraordinary claims require correspondingly careful verification. Some of the apparent excess could potentially be explained by measurement or classification issues specific to this extremely challenging kind of observation. Distant, faint galaxies, whose light has been stretched so dramatically by cosmic expansion that precisely determining their exact distance and true nature remains genuinely difficult, even with Webb's exceptional sensitivity. Researchers studying the individual massive galaxy anomalies mentioned earlier have specifically noted the importance of ruling out alternative explanations, including the possibility that some candidates identified as ordinary massive galaxies might actually be something else entirely, before committing to the more dramatic conclusion that early galaxy formation itself needs to be fundamentally reconsidered. It's worth appreciating just how much of a technical leap this specific mapping achievement actually represents, separate from the theoretical puzzle it's created. Bahram Mobasher, Hatamnia's advisor at UC Riverside, has specifically noted that the large-scale structure identified in this new JWST data is dramatically more informative than earlier maps of the exact same patch of sky captured using Hubble. That's not simply a matter of a slightly sharper picture. Webb's superior sensitivity allows it to detect many additional faint galaxies that Hubble's instruments couldn't pick up at all, while also measuring the distances to those galaxies with considerably greater precision, allowing each one to be placed correctly within its proper slice of cosmic time. That combination, more galaxies detected and more precisely located in three-dimensional space and time, is exactly what allowed this particular team to resolve the cosmic web's filaments and voids in a level of detail that simply wasn't achievable with any previous instrument, regardless of how long researchers spent studying the same underlying patch of sky. So what does all of this actually add up to? The single largest James Webb Space Telescope survey ever conducted has produced the most detailed map ever made of the largest physical structure in the universe, and that map shows the cosmic web already assembled into recognizable filaments and dense galactic clusters far earlier, and considerably more densely populated than any model built before Webb's launch predicted was possible. Whether that gap ultimately gets explained through unexpectedly efficient early star formation, a deeper revision to how dark matter organizes itself during the universe's infancy, or some combination of factors, researchers haven't fully worked out yet. The underlying picture of exactly how the universe's largest structure assembled itself during its first billion years is being actively rewritten, not through a single dramatic announcement, but through the kind of painstaking large-scale mapping project that takes an entire research collaboration years to properly complete. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because the Cosmos Web dataset has already been released publicly for the broader scientific community to study. And there's a real chance the next research team to dig through it finds something that pushes this same mystery even further. Thanks for watching, and I'll see you in the next one.